Hey, good morning, everyone. Can you hear me well? Hey. So I'm Shobha, Shobha Ramu Shivaiah. I'm a senior software development manager with Amazon Music. I particularly head the engineering division for content moderation and business influence and automation for an app called AMP. AMP is a new mobile app that Amazon released. It is a social media app, which is like a live radio where anybody can go and create a show, host a show, or listen to a show. So it's just in the beta release right now, so will be released to public, general public very soon. Prior to Amazon Music, I was with Microsoft as a principal engineering manager for the Azure Compute. And prior to that, I was in UPS for a very long time on the APIs team as a director for external APIs. And I started in the APIs team as a developer, so I've seen the APIs go through the initial stages to all the way up to serving 500 million transactions a day. So I saw the APIs grow along with my professional growth for almost 20 years. So here I am, and today I'm going to talk about system design. System design is a huge concept which probably needs like weeks of learning and months of preparation to understand what it is. I'll just give a brief high-level overview of system design and walk through some key concepts of system design through the API perspective. Like we'll touch about the externals of the API, the peripherals of all the APIs, and how it affects the system. So what is system design? If you have ever interviewed with a tech company or a FAANG company, you probably have prepared yourself with a system design interview. System design is nothing but an organized process of defining the architecture, the data, and the definition for a system. And we are specifically talking about a large-scale system wherein the transaction volume is huge. And system design, again, doesn't solve just the problems which are immediate, but tries to solve the future problems and put your system in a situation where all the anticipated issues can be resolved. It's like a blueprint that you establish right after the requirement phase for the entire system, which you can take and start doing the high level, the detailed design of different components of a system. So let's look at like if you're an engineer, an architect, or even a product manager, these are the different concepts that will go in your head while you're doing a system design. I'll not list it out on this side. We'll dive into each of them while we are going through the next slides. So the first part is scaling. Scaling is where if your APIs are going to get more requests, your systems need to be able to scale. So for the systems to be able to scale, we can do vertical scaling or horizontal scaling. Vertical scaling is where you add more CPU, RAM to your existing servers, so the servers can take in more API requests. And horizontal scaling is where you just go and add more nodes and more servers. Of course, vertical scaling will have its limitation where you can only do so much. Even if you double the CPU, double the RAM, your performance won't be probably double. Horizontal scaling is where most of the large-scale systems implement, where you add more nodes and more servers. So let's look at how horizontal scaling works. So when you do horizontal scaling, there will be a load balancer in front of your APIs. And these, everybody knows about load balancers. So the load balancer can be as simple as it's just round-robining your API requests across the nodes. But usually the load balancer logic is a little bit more complicated. Like I'm giving two examples here just to give you an idea. The first one is like mod-n hashing, where when the request comes in, you do a hash on the request, do a mod n, where n is the number of nodes, and the computed value will determine which node your API request goes into. So simple to implement. However, the disadvantage in that mod n hashing is if you lose a node or if you add a node, your entire request will have to be redistributed. So which means it will take more time for the request to be rendered, and also there'll be cache misses. So the next one that I'm showing there is a consistent hashing, which is a little bit more intelligent version of mod-n hashing, where you do exactly the same, but there is an imaginary ring where you have slots from 0 to n-1, And when the request comes in, you hash the request, you do a mod in, and figure out which slot the request falls in. And then you also take the nodes on your system and do the exact same process where you hash the node, do a mod in, and place the node on the ring. And the way the load balancer will serve the request is it takes in the request, finds the closest node, which is close to your request and in the clockwise direction, and puts your request on that node. The advantage in that is if you lose a node or if you add a node, you will not have to redistribute the entire request, whereas you just need to redistribute a section of it. For example, if the node 2 drops, the request between node 1 and node 2 are the only requests that has to be reconfigured to go to node 3. And if request node 4 drops, the request between node 3 and node 4 will have to be reconfigured to go to node 1. Why is this important? None of us in this room are going to write code for load balance or implement load balance. The reason this is important is as an API team or as an API person, just take a look around you and understand what is happening to the request in front of you. Like how is your load balance, how is your infrastructure set up, and how does the load balance route the request from the client to you. And this may help you do some decisions during design on figuring out like how the requests are coming and how you need to handle. And the next concept I want to touch base is on microservice architecture. This is nothing new. We've been talking about this for decades, especially for this conference, API conference. This is nothing new. But I want to look at this from a system design perspective. So when you design a system, never start with the data modeling or the database. Always start from the front end where understand your customer's need, understand the use case, and then start designing from front to back. So start putting services based on the user's use case, and then design the data behind the services. And of course, when you design the services, think about microservice architecture or monolithic architecture. Most likely than not, for a large-scale system, microservice architecture is the way to go. But it's always important for you to question that and understand why you're going with that architecture versus monolithic. Of course, you know the advantages of monolithic architecture where there's less back and forth between the client and the API and simple to implement, especially if your use cases are just limited and the same use case in your scenario. Microservice architecture is, of course, scalable. So in AMP, of course, we have the microservice architecture, but there are certain services which are doing a lot more than one thing. For example, our user profile service is not only doing the user profile processing, but also storing some PIDs, DIDs, and serving the encryption. Why we did it that way is we wanted to release it earlier, and the negative effects were not much, actually, in fact, none. So that worked at that time, and at some point, we can easily go back and re-architecture that as our use cases develop and we have more time. So always think about that when you do your API design. The next concept I want to touch is proxy servers. Proxy servers, we all know, the main reason for proxy servers are basically to conceal identities. So there's a forward proxy server which conceals the server identity. There's reverse proxy server which conceals the client identity. Along with concealing the identity, the proxy servers can also do other things, like it can have lightweight code like the HTML code or policies or routing logic for your APIs. Proxy servers can act as a cache where they can cache the API request that's coming in and give back the response from the cache without hitting your API. And this helps a lot to save your network bandwidth and the load for your API. And there's also a concept called collapse forwards that can be implemented in the proxy server, where multiple requests that comes into the proxy server can be collapsed into one request, and the one request can be sent into your API. And the response can be sent back to the clients depending on the type of the request. And lastly, API gateway, all of us know about it. These are API proxies, specifically helping us with the API security, rate limiting, and transformation. And again, transformation is huge help in API that if it's implemented in API gateway, where you can actually make a backward compatible change, not breaking backward compatible change in the server, in your service, but then put a transformation layer to keep the clients not backward compatible and give them like a bandwidth and allow them to work for some time and then migrate. The next concept I want to get into is CAP theorem, which is a very important concept for system design. So when anybody starts designing microservice architecture, you want it all. You want performance, you want uptime, and you want resilience. Whereas in a distributed system with a parallel computing, you will not be able to get all three of them. You can only get two of them. And this phenomenon is captured really well with a theory called CAP theorem, where it says out of the three overarching goals, you can only achieve two. So let's look at the three overarching goals in terms of APIs. The first goal is consistency, where you're talking about every API should be consistent in the sense the same API request should render back the same API response no matter which server it's coming from at any given point of time. The second one is availability, where you want all the APIs to be available 100% of the time. And the last one is partition tolerance, where in a distributed network, there can be a network failure. And when you have the network failure, the system is partitioned, where a particular system, a particular partition cannot talk to another partition, so the data is not consistent. So what CAP theorem says is out of these three, you can only get two. For example, think of a system where there's a network failure and there's a partition. If you want to keep the APIs consistent at that time, even with the partition, the only way you can keep it consistent is bring down the APIs until the data is synced up. So you cannot have availability if there's a partition and you want to keep consistency. And at the same time, if you want a partition happens and if you want to keep the APIs available, then you can only keep it available by not giving back consistent response. So, and again, if you want both consistency and availability, then you can almost say that there cannot be a partition for your system, which will never happen in a distributed system. You should always account for network failure. So why is this important for us? This sounds like some question that comes in a bachelor's or a master's exam, right? Very theoretical. Why is this important for us API people in a real professional world? So when you design your APIs, think that this is going to happen. This is your limitation. You are going to achieve only two of them. And think what is important for you. For example, if you're doing a social media API, where your API is giving back the number of likes, number of shares, or a news feed of comments and things like that, consistency may not be that important for you. So if an API on that server gives you back saying there were 1,000 likes, and an API on this server tells you like there were 900 likes, it's okay. I mean, when there's a network failure, it's okay if the consistency is not there. So for that kind, you can kind of give up on consistency and keep the APIs available because you want the social media API to be available without being down. But if you're thinking about a financial API, right, you do not want one API to say $1,000 and another API to say $2,000. So in that case, you want the APIs to be consistent no matter what. So that's where you bring down the API and not make it available until the partition is brought up and synced up. So just knowing this limitation and having that in your mind to design your APIs will really help. And this is a huge, solid concept in system design. Lastly, I want to kind of say that our services, all our services are defined into three different patterns in system design world. The first pattern is replicated services. Replicated services are the most common services we always do, where each service is responsible for serving back a request, and it's replicated in all the servers. They work exactly the same no matter which server, and when a load balancer in front of it doesn't have to think much, it can just distribute the request for the replicated service. Sharded service is a key concept where the service is only responsible for serving a subset of the request. So the load balancer in front of the sharded service will have to realize what is my API request and which sharded service I need to send it to. An example here, like think of a creator API, which is giving back rich attributes, which is location specific. Like a creator API in New York will have to give back New York concerts, New York restaurant details, or the interest of people in New York, like the genre interest and things like that. So the load balancer should know that, okay, this request needs to go to the sharded service for New York to get the creator API data. And they can have a similar service for California, and they can have a similar service for a combined southern state like Georgia, Tennessee, and Alabama, where the population is not much. So the load balancer here decides where the response goes to. And the last one is scatter-gather services. This is a very interesting pattern, not used much, but for certain use cases, it's really helpful, where the request comes into a load balancer. It doesn't even have to be a load balancer. It's like a root node. It comes into the root node where the request comes in and then is distributed to multiple services parallelly. A classic example for that is a loan request, where you ask for a loan, and then the root node will distribute it and send it to multiple banks, gets back the details from the loan, orders it, and responds to you with what is the good interest, or they may even have some tie-ups to show a particular bank on the top, so it can do all those processing. Travelocity, Expedia is another example where you're searching for restaurants, the request comes in, the API that sits there, the root node that sits there can send multiple requests to multiple hotels to get the price range and other details, and then serve. And the best thing is it can all be done parallelly, so quick response. So scatter-gather services is one of the pattern which is like really useful in certain use cases. So just having this idea that your services can be each of them, like it will help you design the service saying, hey, do I need to serve all locations, or shall I just say the service will only care about New York? Or shall I just say like these multiple services will be gathered at a root node and make a system a little bit more complex? And with that, I want to conclude with like a little checklist for APIs with system design perspective. The first checklist first item that I want to talk about is concurrency. When your system is large and you are getting a lot of requests, you are bound to get a lot of concurrent requests. It's not a big deal if it's only read-only APIs, but if you have to update your APIs, you need to keep concurrency in mind. So for example, you get a GET request, and before the update on your REST API, you can you don't want to lock this API, because that will really slow down the system, especially in a large-scale system. So there are two things that you can do. You can do nothing and just let the latest update win, or you can actually do something called optimistic locking, where in the GET API, you can give back a checksum, and then in the update API request, you can get the checksum back. And in the backend, you can see if the checksum has changed, and you can give an error to your user saying, hey, something has changed recently, so please try to refresh again and update. So that kind of helps the use case for concurrency. I have a use case like that where for a particular content moderation use case, like you have multiple operators looking at a use case, and if somebody has entered a decision and somebody is trying to enter another decision just milliseconds later, you can check the checksum and let them know saying, hey, looks like this case has already been looked at and a decision has been made. Do you want to kind of take a look at the latest update on this case? And network, always optimize your API for low latency and high throughput. How do you do that? Define your maximum API request parameter, or define your maximum response size parameter and chunk your responses. And you can even go as far as technical as doing streaming APIs, where when the request comes in, you can set up a streaming API where the responses comes in chunks when it's available. And you can also do defining use case specific endpoint. So for example, if I know that in my use case, the user is always requesting for a show information along with the creator information, I can design an endpoint which is actually giving both together. Like it calls the show API and the creator API and combines and gives it back. Again, it's against a microservice architecture, but it helps the network bandwidth. The time to process both of them will be the same, whereas from the client to the server, there's only one request. So you save time there, you save bandwidth there. And if your 95% of your use cases is that, you serve the purpose. So use that analysis on your API and figure out how you can help network in terms of latency and throughput. Real world performance, I would go as far as saying the best attribute you can give to your API is performance. If your API can perform well, I mean, that's the best characteristics you can give to your API, no matter how nicely you've written the code behind it. So for that, you really need to understand your API's use case, like get out of your API implementation world, understand how it is implemented, what is the load that you're getting, and test for it, and make sure you enhance the performance of the API. With that, hand in hand goes estimation, where it's very important to write down, literally scribble down the estimation for your API throughout in the system design phase, high-level design phase, detailed design phase, implementation, and testing. Write down the numbers, like what is your average throughput request, what is your peak throughput request, how is your throughput distribution by API on hourly basis, how is the distribution by user on an hourly basis. And these numbers will help you design the API better during the implementation stage. And lastly, availability and reliability. Understand what in the system can make your API go down, and understand it really well. And when it goes down, also understand how how you are responding, so how reliable your APIs are. Just thinking through that will help you design the APIs better and have a good user experience at the outside of your world of API. With that, I will conclude my presentation. Thank you so much for listening to me. You can contact me on LinkedIn, Shobha, Ramu, Shivaiah, and I'll also be available here during lunch. So if you have any questions, reach out to me. It was a pleasure talking to you all. Thank you.
Thank you. Questions?
It's an excellent presentation, actually. I'm able to recall everything from system design from end to end. And there's a lot to talk about it, to be honest, right? You know, especially you mentioned about the load balancer way of doing it and hash balancing way of doing it. Again, that's a topic that we can have a special discussion on.
Yes, it was.
Even for the scattered node of API design and versus like, you have three types of API design. I have a lot to talk about it, and I would like to connect with you separately.
Sure, thank you. Yeah, it was hard for me to put this together because each one can be.
There were a lot of topics in there. That was very. So I guess I'll ask a question. I mean, there were so many topics in there, but
yes.
Maybe roles and responsibilities between an API developer and the other roles, the product manager, and so on. I mean, I'll have many APIs. Some of them may need certain characteristics, others need others, right? So how do I organize for that?
Yeah, so I think that's why I'm feeling like the API team will have to look outside of the world a little bit and understand the entire system. Yeah. And that way they know the features that are available, and they can kind of, even though they're doing just one particular world, if they know that these are the different features around me, they can kind of design it that way. So I would say this is not just an engineering role. It's not just an architect role. Even for a product manager or even the marketing manager, if they know the availability of these features and how it affects the entire system, you can question your engineering team or you can question your product team to kind of, hey, why are we not doing this? I mean, pick up this principle. And just knowing about these concepts, I mean, will really help you get the entire system that your API is serving run robustly.
Thank you.
Thank you.
All right, thank you.